All right, and we're back with more series. This has two quick topics. Um, the first one is just some basic properties of series that are useful, and the second one is called the nth term divergence test, which is a test for showing that some series diverge. It's important to understand it will never tell you that a series converges, only that it diverges. And sometimes it works, sometimes it doesn't. Okay, so here's just a pile of equations. Um, it's worth noting if I replace infinity here with some number and I'm looking at a finite sum, these things are always true. And this first one, factoring the seed out, that's just a distributive law. Splitting up a sum is just like addition is commutative. Um, and the last one is just saying if you have a sum and you break it into two smaller sums, the two smaller ones will add up to the whole thing. So they're kind of obvious statements once you whittle them down enough, but for infinite series, it's maybe a little less obvious. And when working with sigma notation, it's good to be able to understand how those properties can be written down using this notation. So the first one, if you have a constant times every term of the series, you can factor it out. Now, this only makes sense as an equation when uh, this is a number, right? If it were infinity or just diverged in an oscillating sense, it wouldn't make any sense to write this down. So we have always this caveat that it's um, when certain things actually exist, then you can pull out the constant. Um, this next one, when both the series of the ANs and the BNs converge, then the series where the first term is A1 plus B1, the second term is A2 plus B2, that will converge to the sum of the ANs plus the sum of the BNs. So that is basically taking an infinite sum and rearranging the terms, which is actually a really hairy thing to do in general. But when these both actually converge, it's not hairy. It's just a thing you can do. So you can split up a more complicated sum into multiple simpler ones. And the last one says, well, we're starting at someplace k and going to infinity. So I could separate off, chunk off the first, um, I guess this is the first m plus one terms of the series, leave it. And then oh shoot, okay, there's a typo right here because I've added up term k plus m twice. It's in both here and here. So this should say from k plus m plus one to infinity. So for example, let's write a little example to make this clear. If the first one was going from 10 to infinity, I could split that up if I wanted to go from, say, 10 to 20. And then the remainder is the terms from 21 to 1 to sorry, to infinity added up, right? So that together makes up all of the terms that we see on the left-hand side. Um, Sorry about that typo. All right, moving on. So let's see how some of those properties work in action. So this is a geometric series, so you should know the answer from last time how to, determine the sum. It's this a over 1 minus r thing, but that's only when your counter starts at 0. So what we're going to do is um, eventually use that, but we have to account for that discrepancy in terms first. And my screen is having a hard time here. 1 second. All right, there we go. So one way I can use that first property is just pull the root 2 outside the sum and not worry about it until the end. And that makes this just a slight bit simpler. So we know the sum from 0 to infinity of 2/5 raised to the n. That's what the formula for a geometric series tells us. And now I'm going to break that up using that third property to go from 0 to 6. And then from 7 to infinity. Right, so that sort of tail of the series from 7 to infinity, that's what we're interested in solving for. Um, so that means we have to figure out what the other two unknowns are, right? So A for this series is 1. R is 2/5, which is less than 1. So it converges to 1 over 1 minus 2/5, which is 1 over 3/5, which is 5/3. So the whole from 0 to infinity is 5/3. And then this is a finite sum, and we just have to add it up. I guess we could leave it like that, maybe, but I'm interested in getting sort of a real answer. So 1 is the first term there, plus 2/5 plus 4 25ths, and well, I might need my calculator. We've done 0, 1, 2, 3 terms so far. We need to get up to 6. So that's 4, 5, 6. And I'm just going to start writing 5 to the 4th, 5 to the 5th, 5 to the 6th, because those are getting to be pretty big numbers. All right, great. I'm going to just get a decimal for that real quick. All right, so just for notational purposes, let's call this big number C. So the conclusion of this line here is that the sum from 7 to infinity of 2/5 raised to the n is equal to 5/3 minus that partial sum C, and that is 0.0027. And then that means the final answer is root 2 times that number, which is roughly 0.0039. Okay, so that hopefully illustrates how some of those properties can be useful in practice. And let's move on to the nth term divergence test. So the idea here is that in order for an infinite sum of numbers to add up to a finite amount, the numbers we're adding need to get smaller and smaller. Um, and kind of a nice historical example is Zeno's paradox. So you've probably heard some version of this at some point, and it's from ancient Greece. Um, Zeno actually had three paradoxes, but this is the most famous one, where Achilles is racing a tortoise. Achilles is very fast, so he gives the tortoise a head start, let's say 100 meters. But before he can catch up to the tortoise, he must first get halfway. So he has to run 50 meters to get halfway. During that time, the tortoise walks forwards maybe 4 meters, a small amount. Um, and so now they're 54 meters apart. So Achilles is going to run, chase that tortoise, but before catching up to him, he has to get halfway again. So this continues in an infinite cycle. And how can he catch up to the tortoise infinitely many times, right? How can anyone do infinitely many things? Um, Now, obviously, the Greeks knew this was possible because they'd run races before. The issue is more like, how do you fit this into your mathematical framework of understanding motion and understanding just like how things happen over time? Um, this sort of question could be applied to basically any situation. So, it was kind of like a what's going on here question, and this question is answered by infinite series. So, um, as we know, infinite sums can come out to a finite amount, but the terms need to be approaching zero quickly. And not so much the quickly part, but they must be approaching zero is the idea of the nth term test. So it says that if you have some series and the terms are not approaching zero, then it definitely diverges. And again, this doesn't ever tell us whether it converges, um, or that it converges, but it can tell us that it diverges. So, um, example, we're adding up the terms n over n plus 1, where n goes from 1 to infinity. So let's write out a few terms of this sum. The first one is 1/2. The second one is 2/3, and then 3/4, etc. Right? Um, so given any series, we can ask, what does the nth term test say about this series? And that means I need to try the test and see it might work, it might fail and not tell me anything, but just evaluate what happens. So in order to do that, I have to evaluate this limit as n goes to infinity of the terms of the series, and that limit is 1. So 1 is not equal to 0, right? So according to the nth term test, the series diverges. Now, this is, I mean, kind of a common sense idea, right? Because if the terms I'm adding up are getting closer and closer to 1, the further and further we go out in the sequence, then eventually, you've added up all these numbers, and eventually it's approximately just adding up 1 plus 1 plus 1 infinitely many times, which we already said that that should certainly be infinity, right? Um, so this diverges to infinity. Now, oops, this way. So one thing to point out is that it could be here that the limit doesn't exist, and then this term this test still says that the series diverges. It doesn't necessarily diverge to infinity, but whether this limit exists and it's a number that's not zero, or whether the limit doesn't exist at all, you can conclude that the series diverges. You may have to think harder about, is it diverging to infinity or not? Okay, example 2. This is a geometric series, right? R is 12/13, which is less than 1. So I know by the geometric series test that this converges. However, that's not the question we were asked. So we were asked, what does the nth term test say? So I have to try the nth term test. So I do limit as n approaches infinity of 12/13 raised to the n. Now, if you have any number that's smaller than 1, for example, 1/2, and you start raising it to higher and higher powers, it's going to get smaller, right? It's going to eventually approach 0. And that's what's happening here too. 12/13 is less than 1. So if I raise it to larger and larger powers, it will get closer and closer to 0. So in this case, the limit is 0. And that means the test fails and does not tell us whether or not this series converges. We know for a different reason that it converges, but the nth term test doesn't answer the question. So we can just say the test fails. We don't know from using this test whether it converges or diverges. Okay, great. So here's an example. Try the nth term test on this series and answer that specific question. What can you conclude from this test? So give that a whirl, pause the video, and here is the answer. If you evaluate that limit of the terms, they're going to approach -3/7. And we did an example similar to this on the last video. If you don't know how to compute that limit, go watch the previous video. But the limit is -3/7, which is not 0. That means by the nth term test, I know that this series diverges. All right, that's all for today. Have a good one.